you recall, in Chem 1, we talk about light as a demonstration of the conservation of energy law. That whatever energy is absorbed by electrons to make them jump is what's released when they fall back down. Although recall, some types of energy are so high that they jump up and they can't come back down because they've stretched out past beyond the attraction of the nucleus. But that's kind of our principle allowing us to do a lot of what we're doing here. Recall a photon is that kind of energy packet, if you will, absorbed by the atom that causes energy to release. What I wanted to let you know about is these two equations on the bottom. And these are the two equations that will be given to you. However, typically, this first equation is written as C equals lambda times mu. So it's not a division equation. However, this is typically how you're going to use it. Now, if you don't remember what these symbols mean, the thing that looks like a V, but actually isn't quite a V, if you look close enough, it's not straight like a V completely. That's the Greek letter nu. That stands for frequency. Remember, frequency is how often a wave occurs. The lambda, then, this letter here, is your wavelength. And in Chem 1, we went over the fact that you have to know your wavelength in meters. Because two other things that will be given to you, and I did not type down on this slide, is the speed of light, for example. They give you as 2.998 times 10 to the 8th meters per second. In Chem 1, we called it 3.0. For some reason, AP wanted to give you 4 sig digs on the speed of light. So in other words, to use that first equation, if you were given either the wavelength, which is lambda, or the frequency, which is nu, you could solve for the other because the speed of light is a constant. And again, that is given to you on the top of your equation sheet. The second equation is used to solve for the energy then. So for example, if you're given a question where we set our spectrophotometers at 630 nanometers last class, I could ask you for one individual photon, how much energy is in that wavelength. You could first take your wavelength, your lambda, and solve for nu. What's nu? C over lambda. Then from there, you could plug that frequency into this equation to solve for energy. Now, H is another constant that is given to you. This is Planck's constant. And once again, for some reason, they gave you one more sig dig than we give you in Chem 1. 6.626 times 10 to the negative 34th. And the unit is a joule second, which that unit really doesn't mean much of anything. However, frequency is how often something happens. So if that's how often something happens per second, when you multiply Planck's constant, which is this letter H, times frequency, the seconds part cancels out and you're left with joules as your final unit. That's the rationale behind that unit. Heck, remember the unit for the ideal gas law, liter atmospheres per mole Kelvin? That means absolutely nothing. That unit was just put in there to cancel out other units so mathematically you get to the right response. So again, these two equations, these constants will be given to you. We have to know how to manipulate them to solve for what we need to solve for. And again, don't forget to convert to meters if we have a wavelength. Wavelengths are typically in nanometers. However, in order for units to cancel out with the speed of light, which is a meters per second, you have to be in meters. Okay, so don't need to worry about that first bullet point at all. Electrons, again, ejected from the surface of certain metal. This is a photoelectronic effect. What I want to do to wrap up notes here is the second bullet point. I want to solve a question. This question says energy needed to dislodge electrons from sodium is 275 kilojoules per mole. What wavelength of light per photon is needed to cause this? So this kicks it up a notch beyond what we have done before in Chem 1. So I'm going to kind of switch over to Smart Notebook here and show you how to calculate this type of problem. And then that's our notes. Again, then we need to practice the math a little bit at that point. So what I was given to start off this problem is 275 kilojoules per mole. If you recall in Chem 1, we had no mention of kilojoules. We had definitely no mention of moles when we did light calculations because we tried to simplify the process. However, when we simplified the process, and I know it because in Chem 1 right now we are going over light calculations, we'd get weird answers like 2.5 times 10 to the negative 19th joules. It'd be this ridiculously small number because it was for one photon. The odds of doing this for one photon are pretty low. Again, when we turn on the lights in here, there's a lot of atoms right now that are shining down on us. So it makes more sense to actually report it in kilojoules per mole. We were just trying to eliminate some of the steps for Chem 1. So the first thing I want to do is get rid of moles, which is almost the opposite of what I tell you to do in general. When it don't convert to moles. To get rid of moles, I need moles on the top. And this is where Avogadro's number would be used on the bottom. Again, I usually call it 6.02. I believe the AP sheet gives it to you as 6.022 instead of 23rd. Not only that, because again, hopefully you're comfortable with the fact that units cancel out. Moles now on the top and the bottom cancel out. If I took 275 divided by that, that would give me my number of kilojoules. I'm going to get rid of the kilojoules part as well. So my step one is I'm going to try to get rid of the stuff that AP is making you do to go back to what we did in Chem 1. So if I want to get rid of kilojoules, I need kilojoules on the bottom. That way it cancels out with what I have on the top. And then joules on the top. Remember, joule is a unit of energy. Just like a calorie is, but we are not drinking soda, we're in a science class. Kilo is a metric prefix, where there's one of those for every 1,000 of whatever base unit you choose. Again, I will show you this math right here. This would get me, I'll keep my 3 sig digs there, of 4.57 times 10 to the negative 19th joules. Now that's the type of answers that if we gave you a wavelength, you would have solved for in Chem 1. What I'm basically doing is the exact opposite progression. However, the joule number still kind of matches what we typically solve for in Chem 1. So now we have an energy. Joules is a measurement of energy. Now what I can do is use this equation. But I'm going to solve for frequency, which is the Greek letter nu. So in this case, that's going to be my energy divided by Planck's constant. So if I find that energy value right there of 4.57 times 10 to the negative 19th joules, I'm going to divide that by Planck's constant of the 6.626 times 10 to the negative 34th joule seconds. That would give me 6.89 times 10 to the 14th. The unit for frequency is a hertz. You tune it on your radio in your car. Like, I think 105.1 right now is playing Christmas music. They started this a couple weeks ago, which is kind of obnoxious, but okay, that's their choice. If you tune into the 105.1, they actually have a unit after that, a capital M hertz, a megahertz. Mega is just a metric prefix. So that is a specific frequency that their radio signal is being sent out on that your antenna can pick up and now listen to that music. Hertz values, frequencies are usually huge numbers. Notice the big power of 10 there. Because waves of light are super duper small if they're especially high energy. Now radio waves aren't nearly as big, but still they're fairly big. So now I have a frequency. This question originally asked me to solve for wavelength. Remember, the other equation you're given is this equation. However, we're going to solve for wavelength, which is lambda. So this is going to equal the speed of light divided by frequency. So, speed of light is 2.998 times 10 to the 8th meters per second divided by 6.89 times 10 to the 14th hertz. And this would give me 4.35 times 10 to the negative 7th meters. Now, if it does not give you the unit that you need to solve for, you could be done with this question. However, I want to remind you of the nanometer conversion as well that we went over in Chem 1, because typically light is measured in nanometers. And remember our spectrophotometer, for example. So I'm going to cap this off with a metric conversion as well. Where if I want meters to cancel out, I need meters on the bottom. That puts nanometers on the top. There are 10 to the 9th nanometers in 1 meter. Nano 9. Plus now this gives me a much more readable value, 435 nanometers. Heck, that's something we can set our spectrophotometers at. That's violet on the electromagnetic spectrum. You should be able to either take the path that I just showed you or the reverse path. The reverse path would be starting with a wavelength, and again, if we give it to you in nanometers, you got to convert to meters. But then, if I continue on that reverse path, I would then have to find the frequency, and then with the frequency, I could solve for the energy, and then if I have the energy, I can convert my joules into kilojoules, and then also kilojoules per mole. So I'm hoping that we can spend a little time today in class reviewing the two equations, but then also we got a little extra to tack on here. We need to be comfortable with that. And I tried to show this in a matter of conversions. Again, kilojoules canceled out here and here. Because if you can get used to converting from one unit to another, that's a lot of the math that we do anyways. I mean, remember stoichiometry is coming up next unit full blown. That's all about canceling things out. So a similar thing of, do we know some of these equalities? Again, I believe Avogadro's number is given to you with 4 sig digs. The only thing that's not given to you on the equation sheet is metric conversions. So knowing that there's 1,000 of anything in 1 kilo of anything, 1,000 meters in 1 kilometer, 1,000 joules in 1 kilojoule. And then also knowing the nano prefix as well in order to do that bottom conversion is also important.